All right, so quantum field theory. So to start, we're going to start with just regular classical mechanics a la Newton. So we have a ball here and it is moving through space, and we can describe it using its energy. So we can write down the kinetic energy, which is 1/2 mv squared, m being the mass and v being the velocity. And we can rewrite this as 1/2 m times the derivative of the position, so dy dt squared, velocity being the derivative of position. We can also write down its potential energy, so V equals mgh. So here in this case, m is again the mass, g is the acceleration due to gravity, and h is the height. I'm just going to rewrite this as mg for simplicity. Okay, so basically all this means is the higher the ball is, the more energy it's going to have when it falls to the ground, because it will have longer to fall and more time to increase its velocity up to the terminal velocity. Okay, so in classical mechanics, we have something called the Lagrangian, which is a very powerful mathematical tool. Basically, it's the Lagrangian equals the kinetic energy minus the potential energy. And I wrote that as V, so oops, Ke minus V. And some really smart people developed something called the Euler-Lagrange equation, which tells us that the derivative of the Lagrangian with respect to position minus the time derivative of the derivative of the Lagrangian with respect to velocity equals 0. Now, in this case, this is not going to give us a very exciting result, but I'll just work through the math really quick just to show you. So dl dy equals, oh, I need to write down our Lagrangian really quick. I should have done that before. I'll write it over here. L equals Ke minus PV. So that is going to be 1/2 mv squared minus mg y. Okay, cool. And actually this g should have a minus sign, so that's confusing. So this should have a minus here, because acceleration due to gravity pulls the ball downwards. So this actually is going to have a plus sign. Okay, cool. Yeah, so our derivative with respect to position, we only have to worry about this term because there's no y's in the other term. So this is just going to be equal to mg. Our derivative with respect to velocity is just a simple derivative here. So 1/2 mv squared, this we pulled the 2 down, so it's just mv. And then if we do the time derivative of this, d dt of mv from this term, we're basically taking the time derivative of the velocity, which is the acceleration, because velocity, like the change in velocity with respect to time, is the acceleration, and that's how the derivative is. So, and the mass stays constant, so we have ma. So what we get with the Euler-Lagrange equation is 0 equals mg minus ma. G is the acceleration. So you get 0 equals 0. Cool, the math works. And this, of course, works for every classical system. Oh my gosh, I'm already 4 minutes in. But yeah, this works for pretty much every classical system, and it is basically the formulation that we use for all of classical mechanics. Now, some very smart people in the early 20th century, like Schrödinger, realized that we could do this same thing using wave functions. And this is pretty much the formulation of quantum mechanics, which I'm not going to get into a ton, but basically we have this new thing called psi, which is the wave function. And the wave function tells us all about particles moving around in space. So every particle has a wave function, like we have an electron here. The electron has a wave function, and the wave function basically tells us the probability of the electron being in this position at this time. So the electron has some coordinates x, y, z, and it exists at time t. And the wave function tells us how likely it is that the electron will actually be in that place at that time. Okay, so then skipping over all of quantum mechanics the problem with it is that it does not include Einstein's theory of special relativity, which is super important because basically time doesn't exist the way that we think it does. Relativity sort of messes all things up, including the passage of time and how fast it moves. You can't see, but I wrote some notes over here because I needed to refresh on all of this. But this is good. Refreshing is good. Okay, so Einstein's theory of relativity gives us something extremely important, which is the Minkowski metric. Not going to tell you how this is derived right now, but we can chat about it in person if you are interested. But basically it is a matrix of ones and zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And this matrix describes space-time. So this right here is our time. And then we have the 1, 1, 1 is x, y, and z. This is going to make more sense in a sec. This is not really a great way to explain this, but here we are. Okay. So the Minkowski metric basically describes the way that space-time behaves mathematically. So there's this extra minus 1. I know this was kind of the whole question, and I'm not going to explain it right now because it's a lot. But that minus 1 exists, and without it, our math would not work. So the Minkowski metric basically tells us how to combine quantum mechanics with special relativity, which is quantum field theory. Which is a really cool thing, and it is sort of the foundation of all of modern particle physics. So we love quantum field theory. Yeah, and it's quantum field theory. All it is it's quantum mechanics. I already said this. Now I'm rambling. Plus special relativity. Using this Minkowski metric and also this Lagrangian formulation. So what we do in quantum field theory is for a particle like an electron, we have its wave function psi, which tells us about the probability of the electron being in some place at some time, which is kind of like this ball. The kinetic and potential energies sort of tell us about where the ball is going to be at some place and some time. So the wave function is kind of like the velocity and position variables up in these equations up here. It's a little bit more complicated, of course, but it's similar. Okay, so a bunch of really smart physicists a little later in the 20th century, around like the 50s, including Pauli, derived what the kinetic and potential energies would be of particles like electrons. So they found that the kinetic energy would be minus c h bar psi bar gamma mu d dx mu psi. Now, that looks horrible and scary, but these guys are just constants. These are the field, the wave function. Gamma mu is a matrix that kind of makes the math work out. And this d dx mu is our derivative. Which the derivative tells us about the velocity. So actually, this equation looks kind of like this equation up here, our 1/2 m d dy dt squared. This d dx mu takes the place of that d dt. We have two copies of the field, which in this case is y. So we have y squared here, and we have this psi bar psi here. And then we have constants. So in this case, our constants are 1/2 m. This case, our constants are a little bit more complicated, but that's okay. And you can kind of just think of that gamma matrix as a function also, or sorry, as a constant also. All right, then our potential energy is minus mc squared psi bar psi. So this again looks very different, but is actually not that different. We have a mass still, which we had up here. And we have a c squared, which sort of follows us around a lot in quantum mechanics and quantum field theory. That is just the speed of light. And then we have our wave function. Okay, I need a new page. Let's see. I'm almost done, I promise. So when you plug those kinetic and potential energies into the Euler-Lagrange equation that I showed before, that thing with the derivatives and the Lagrangian, you get the Dirac equation, which is gamma mu d dx mu plus, looking at my notes now, mc over h bar psi equals 0. So this equation basically tells us everything we need to know about electrons. It's a super powerful, oh, my focus is not, it's getting dark. I was using the sunlight, but now, hello? Okay, this is coming in 3 parts apparently. Gonna fix my lighting. Oh, there we go, never mind. Nice. Okay, so this Dirac equation basically tells us everything we need to know about the electron and other particles like it. It tells us where it is, how it behaves, how it interacts with other particles. That's a bit of an overgeneralization. This is sort of like the simplest version because in actuality, the Lagrangians are much more complicated. Like the Lagrangian of the standard model has like 18 terms or something. But it all comes from this formalism. Okay, so the very last thing is how does that Minkowski matrix, this one, which has the -1, how does that play into the Dirac equation? It comes into the Dirac equation with this d dx mu. So what this actually is, oh, I said I was going to explain this before, but I'm explaining it now. So d dx mu, oops, the mu is just telling us that we need to multiply by the Minkowski matrix. And actually that Minkowski matrix is sort of, gets more complicated when you include general relativity, but for now, we're just gonna have this -1. So it's gonna be -1 plus 1 plus 1 plus 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, times our 4 vector of the derivatives. So that is going to be dt, oops, this should be d dt, d dx, d dy, d dz. And this 4 vector thing, that's what this is called. This comes up all over the place in quantum field theory. It's a very, very common mathematical construction. But the 4 vector is basically just a compactified way to write out things in space and time using one variable. So what this gives us is, if you remember your matrix multiplication, it's going to be minus d dt plus d dx plus d dy plus d dz, which if you plug this into this equation up here will give you the full Dirac equation. And yeah, that's basically it. So this -1 makes physics work. Quantum field theory would not work without the -1. We would get nonsense solutions to things. So we need it. And basically, even though we combine time and space into one thing, sort of, in these 4 vectors, the time part is inherently different because it has a -1 and the spatial parts do not. So I don't know if that was very interesting or enlightening, but yeah, that's it. Quantum field theory. Nice job.